All right, so in this lecture, we will introduce computer logic. Before we do everything, we have to, which is something we cannot skip, which is Boolean algebra. You'll see this in probably every computer logic textbook in the world. Okay, Boolean algebra. And so this video, we are going to cover the fundamental Boolean algebra, the fundamental logic being used in computer systems. For example, the OR logic, AND logic, and NOT logic. And then in the next lecture, we are going to introduce some more advanced logic like XOR, XNOR, NOR, things like that. But all these things are based on the fundamental logic like AND, OR, and NOT. So let's learn this first before we go further, right? So in AND logic, usually the operator is a dot or a cross, like multiplication, or just nothing, all right? Just nothing. OR logic, usually it's a plus sign. NOT logic, for example, you have a case A NOT will be a bar on the top. Or sometimes it's going to be A prime. It's also A NOT. Okay. And there's some fundamental things you need to know, right? Because computer is a binary system, and binary numbers are the only numbers the computer can understand. You can also have a decimal number, you can have a hex number in the computer, but however, they are all represented by binary numbers being stored in the memory. Okay, so that's why the Boolean algebra is a operation which deals with zero and ones, the operation between zero and ones, all these binary numbers. So now let's take a look at that. If we have 0 and 0 for this very simple operation, what is the result for this? So it's going to be 0. 0 and 1 will be 0 as well. Okay. 1 and 1 will be 1. 1 and 0 will be 0. So that's the AND logic for all these possible combinations of zeros and ones. It's kind of confusing in the very beginning, but however, all these zeros are being implemented in the computer system by using a ground, which is voltage 0 or logic 0 in the circuit, and 1 is actually can be 5 volts, sometimes can be 3.3 volts. So they are all logic high. It's a high voltage over there. So you have ground, which is 0 volts, and logic 1 can be 3.3 volts, can be whatever which is larger than 0, which is defined as a logic high. So 0 is usually it's a logic low. 1 is so logic high. So it's a relatively higher voltage in the circuit, and you only have these two in a digital system or a digital circuit. These two logic or voltages are the only two voltages you possibly will exist on the board. 0 volts, or can be logic high, which is 3.3, or 5 volts, or something else. Whatever is being defined as a logic 1 or logic high. Okay. So how to remember this? It's kind of confusing. So why 0 and 0 is 0, 0 and 1 is 1, and so on and so forth. So there's one example can make this kind of thing easier. Okay, you can imagine if you are a coach for a basketball team or something, and you have a team, right? You can pick up whatever player you want be on the team. So if you have a really bad player, which we label that player as bad, and another bad player, if you have these two players, it's an AND logic, which means you have to have these two bad players on the court at the same time. Okay, so definitely you will lose a game. So 0 here on the right side of the equation means lose the game. Okay, and if you have a 0 and you have bad player and a good player, so here means it's a good player. If you have a bad player and a good player on the team at the same time, you will lose the game as well. So the reason is this bad player just do anything can make you lose. For example, this guy is keep shooting to to your own basket, to make the other team to to make score to score. So this bad player is really bad. Okay, so it's gonna make the entire team to lose a game. And if you have two really superstar good players, and you'll win the game. If you have, this is the same case, right? So 0 bad and good, good and bad is the same thing. So you lose a game. So this can be, can be used as example in the very beginning when you are trying to, memorize or learn this a little bit faster. Hopefully this can help you a little bit. So the same rules can be used for the OR logic as well. If you have 0 or 0, 0 or 1, 1 or 0, 1 or 1. Now let's use the same logic, same example, see if that makes sense for this case. So that's the OR logic, right? So 0 or 0 is 0. So if you're a coach and you don't have choice, right? So you have two bad players, this guy or this guy, just pick up one, okay? Both of them are bad, so you'll lose a game. And for this case, you can pick up the bad one or you can pick up good one. So of course you want to pick up good one to win the game, right? So you can, for this case, you will win the game. The same thing here, good one or bad one. Of course, pick up the good one, so you will win the game. And two good ones, of course, definitely will win the game. So try to use the example if you find yourself having a hard time to memorize these things in the very beginning, but you will be used to this in the future. It's super simple. But in the very beginning, feel free to use this kind of more practical example or whatever example you are going to develop yourself. As long as you can, it's going to help you to memorize this thing, right? And now we can make another thing, right? So that's AND, that's OR. And now let's take a look at NOT, right? So 1 NOT is going to be 0, 0 NOT is going to be 1. So which means true, or the inverse of true is going to be false. Inverse of false is going to be true. Or 1, if you invert it, you got 0. You invert 0, you get 1. So all these things are not something like just a concept. They are not, okay? So they are physical circuits everywhere in the modern digital system. For example, your smartphone, the laptop, the monitor, everything. Whenever they have a digital system, they have all these logic operators being implemented by hardware or physical circuits or IC chips on the board. Okay, so the NOT, for example, the NOT logic is implemented by the inverter, right? And AND is actually implemented by the AND gate, or OR gate is going to implement the OR logic. So we're going to learn how to design all these circuits in real life. So they are actually super useful. It's not just a concept being used, virtual stuff. They are not. They are physical circuits in there. So we can summarize everything up in the table if you like. So make sure we can remember this, and you will be good at it in the future. Okay, so now, for example, OR logic. So we can have 0, 1, A. A is the case, right? Can be 0 or can be 1. A naught, which is in inverse of A. And now in the row we have 0, 1, A naught. Now let's make a table, right? And let's see all these OR operations for all these things and what are the results. Okay. Sorry, I have really terrible drawing. So 0 or 0, what's the result? So two bad players, no choice, right? So you are going to get the 0. 0 or 1, you have choice. You just pick a good one, you win the game. 0 or A. So in this case, since A is a case, right? So it can be 1 or can be 0. Let's make examples and see what's the result. So if A is 1, 1 or 0 is going to be 1. If A is 0, 0 or 0 will be 0. So actually the final result is A. Whatever A is, after the operation is still A. It's the same thing for A, so we call it A bar or just A naught. Same thing can be if we treat the entire thing as a black box. It's the same stuff, right? So A or 0 is going to be A bar or 0 will be A bar. And what about this one? 1 or 0, you have a choice, pick up a good player, you'll win the game. And 1 or 1, definitely win the game. 1 or, so if you find out the 1 in there, in the OR logic, you'll get a 1 for the result because you have a good player as a choice and you don't have to pick up another one, all the other ones. So just pick up the good one, you'll win the game, right? You don't even need to look at it. You just put a 1 there. The same for this column. 1 or everything is going to be 1. Okay. And A or 0, we had this before, so it's going to be A. A or A. If A is 1, we got a 1. If A is 0, we got a 0. So it's going to be A. A or A bar. If A is 1, A bar will be 0. We got a 1. If A is 0, A bar will be 1. We are still getting a 1. So it's going to be 1 here for this operation. So A bar or 0 is A bar. We had this before here. Okay. A bar or A, we had this one just now, so it's going to be 1. A bar or A bar is A bar. Okay. If you couldn't remember this, just give examples for to A. Can try 1 and try 0 and see what's the result for it. So that's for OR logic. We summarize everything in the table. So what about AND? We have 0, 1, A bar. We have 0, 1, A bar. Table, boom, 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 boom. All right. And logic, no choice. You have to pick up both, right? So if you're a coach, if I was a coach for the basketball team, you're looking at these two bad players, no choice. They have to be on the team at the same time, okay? And whenever you have a 0 in the AND operation, you actually don't need to look at all these. What's the other case in there? You just put a 0 because you have no choice. And this bad player is really bad. He's gonna keep shooting to your own basket to let other people to win. It's the same thing for this column. And now let's take a look at 1. 1 and 1, two good players on the team at the same time, great. And 1 A. So if A is 1, you got a 1. If A is 0, you got a 0. So it's literally just A. Depends on A. See if you can win the game. If A is good, you will win the game. If A is bad, you lose the game. So, if you treat the entire case as a box, black box, so A bar is the same stuff, right? Just put A bar here. And now we have this, I believe, here. So it's going to be A, right? We have this here before. And now A and A will be A as well. A and A bar. If A is 1, A bar will be 0, right? And you are going to get a 0. If A is 0, A bar will be 1. You'll still get a 0. So it's going to be 0. And A bar and 1 is A bar is A, 0, A bar and A bar is A bar. Right? So this is how you work. This is pretty important. This lays the groundwork for all these things you're going to learn in the future. So make sure if I give you a table, you're able to fill out the table with all these correct results for the logic operation here. Super important. So the next step, we're going to find out some logic operations with the cases A bar, A, B, C, like this, and what are these operation laws to which are give you the rules for doing these operations. So the first one, I want to say it's A and B equals to B and A. Okay, keep in mind this is one of the rules. It's pretty similar to the multiplication in the regular operations. You have 10, for example, 5 times 10, we definitely know is equals to 10 times 5, right? It's going to be 50. Same stuff. Pretty similar, okay? So A and B is a B and A, it's the same thing. The second rules is A and B or C equals to A and B or A and C. Okay. The third one, A or B equals to B or A. Just fundamental ones. We're not dealing with complicated ones, and we will work on these more complicated ones in the future, but not right now. Okay, this is just the first lecture for Boolean algebra. We, no, we are not doing too much. And do we have one more? Probably we can stop here because that's the most important things I want you guys to know for this lecture, and make sure you understand this, and we get a little start here so you know what we need to know in the future, and we'll give you more examples on all these rules for doing Boolean algebra. Because it's super important, we need these rules to simplify a logic into a simpler logic, and so we can simplify the circuit in the future. Okay, so that's it. I'm gonna see you in the next video, right?